Welcome, everyone, to my next talk in the Science of Religion series. And as you can see, this talk is on the solar system. So if this is your first time to my talks, my name's Dr. Christina Sweeney Hillesheim. I have a doctorate in chemistry, but I also have a master's of divinity in apologetics. And so this talk, we're just going to look at our solar system. And the previous talk that was right before this one was on the Copernican principle. And so the Copernican principle talks about how our universe or our galaxy and our solar system is not very special. It's just common, nothing is unique about it. So we're going to dive into our solar system and then you can come to the conclusion if you think, is it unique or is it not unique? So let's start. So let's talk about our galaxy first. So there are three different types of galaxies, kind of basic forms or types. In the universe, there are spiral galaxies, elliptical galaxies, and irregular galaxies. And I'm going to talk about each one individually. So first, let's talk about spiral galaxies. So our Milky Way is a spiral galaxy. So we live in a spiral galaxy. And so it's considered a spiral galaxy. So in the center of this kind of has a central spherical bulge with a disk. And then you kind of have these little like spiral arms extending outward from this nucleus, this central point, in like a spiral pattern. So if you've seen one of those like pinwheels, the ones that you hold and you blow and they kind of spin, it kind of looks like this, but think about a star kind of space version of a pinwheel. So that would be a spiral galaxy. So then our next question is, well, is a spiral galaxy going to be really good for people to live in? Like, would it be habitable? So the spiral galaxy does provide what we would consider a safe zone. So a zone that's kind of safe for life, where in our case, this is where Earth is located. It's located in this safe zone, which is why life has been able to flourish and be able to continue in this spot. As you can see it where the sun is, that's where we're at. And I'll talk about it a little bit more on the next slide as well. So you'll be able to see it better. So when you have galaxies, galaxies have varying degrees of star formation. And so remember when we talked about star formation, this is when your interstellar gases are going to coalesce and we're going to form stars, star clusters, and even massive stars. But you're also going to have in this area where supernova. So supernova are going to be when, the stars are exploding. So star formation isn't necessarily is a very dangerous place to be around. So if you have active star formation, you don't necessarily want your planet to be in that area. Okay, so in our case, wherever you have that star formation, you're also going to have a lot of supernova exploding. And where this is located is in these little spiral arms. So in these spiral arms are where this star activity is the most prevalent. So that would be a very dangerous place for us to be. We don't want to be within those spiral arms. So it would be safer for us to be outside of these spiral arms, which is actually where we're located. Also inside these spiral arms, not only is the star formation very high and active, but there's also a lot of hazardous giant molecular clouds. So there's a lot of stuff that's going in these spiral arms that just makes life not very possible or probable. So we exist between two of these spiral arms. And so between the Sagittarius spiral arm and the Perseus spiral arm. And you can kind of see that it's this little bright dot. And I'll use my mouse here to show you. So this is where we're located in our galaxy. So you can kind of see we're safely kind of cocooned in between these two spiral arms. So if you also want to look at it, you can also see, well, how are we in comparison to the middle? So Earth is actually very far from the nucleus of the galaxy, so from the center of the galaxy. And so there in the center is actually a massive black hole. So there's a massive black hole at the center of the galaxy. And we've actually learned from the Hubble Space Telescope that almost every large galaxy that's nearby us has a giant black hole at the center of their galaxy. So this is very common. It's not, that part is not necessarily unique to our galaxy. So you might say, okay, cool, black hole in the middle. Well, even though there's a black hole, most of these black holes are inactive. However, if something gets kind of near them or falls into them, it's going to get torn up by tidal forces, by very strong tidal forces. And also, when this happens, these black holes are going to release a lot of high energy. And so, when I talk about high energy, I mean like gamma rays, X rays, and particle radiation. So, these are things that you don't want to, be around. Anything that's going to be in this inner region that's going to be close to this black hole would then be subjected to those high levels of radiation, which also would not be very good for life. Additionally, in the center, there's going to be more supernova exploding. So, more supernova exploding, so even more of a dangerous spot, more reasons to not want to be close to the center. So, as you can see, we're far away from being in the center of that galaxy. So, we're not only in a spiral arm, but we're also at a good distance away from the center and from that black hole area. So, what else is good about where we're located and about being in a spiral galaxy? So, the composition of a spiral galaxy actually changes as you go from the center outward. So, the abundance of heavy elements is actually greater towards the center due to that active star formation. So, remember, we need heavy elements. For planets to form, you need the heavy elements. And so, how do we get the heavy elements? That's from star death. So, you start with hydrogen and helium, and when they come together, and then as the stars kind of become supernovas and then they die off and then they create new stars, as the stars kind of go through their life cycle, that's when we start to get heavier elements. So, since there's more active star formation in the center, we're going to have more of the heavy elements in the center. And then as you get further out, you're going to have less of those heavy elements. So, in the outer disk of the galaxy, star formation has still been happening, but it's going on slower and less frequently. So, that's why we have less heavy elements there. So, in the middle, more heavy elements. On the outside, less heavy elements. And so, those outer regions are actually less likely to have Earth type planets. And so this is kind of a unique thing with our planet that we are farther away from the center, but we still were able to have enough heavy elements to be able to have an Earth type planet. And so this is one of the things that is kind of unique in our situation because you wouldn't expect to see that. You would expect any Earth type planets to be closer to the center. But in our case, we have one. All right, so let's go and talk about the elliptical galaxy. So you might say, okay, I got it. Spiral galaxies, we need to be in between those spiral arms and not too close, but not too far away from the center. That's like the sweet spot. All right, well, but what about elliptical galaxies? So elliptical galaxies are actually the most common type of galaxy. So most of them are going to be in this kind of egg-shaped format. And the way that the stars are here, they're kind of very random. The orbits aren't going to be elliptical or circular. They're kind of all random orbits, like bees kind of swarming a beehive. Excuse me. So would an elliptical galaxy be a good galaxy for a planet, for habitation? So because the stars are kind of in this little beehive swarming kind of pattern, the stars actually visit every region, which means they're occasionally going to visit that dangerous, dense inner regions where that black hole may be active. So remember I said we want the star, which would be where our planet, our Earth-like planet would be, rotating around that star. We want that star to not be around the danger spot. Okay. And so, but in this case, at some point, it's going to be near the danger spot. So that is not very good in our situation if we want to have an Earth-like planet. Also, elliptical galaxies lack the heavy elements needed to form Earth-like planets. So elliptical galaxies, they're less massive and they're less luminous than the Milky Way. So to kind of give you a perspective of this, the Milky Way, our spiral galaxy, is on the top 1 to 2% of the most massive and luminous. And so the bigger the galaxy, the more heavy elements it can have. Because it has that stronger gravity, it's going to be able to attract hydrogen and helium and be able to cycle through them to build up these heavy elements. Whereas in these low mass galaxies, which make up the vast majority of galaxies, they're this lower mass galaxies, you could have whole galaxies without even a single Earth-like planet because they didn't have enough of these heavy elements to really construct something that would be Earth-like. So in the last talk that I ended with the Copernican principle, at the end of that, I talked about kind of star clusters or globular clusters. And so just like a globular cluster, you could have a whole cluster, a whole bunch, thousands and thousands of stars, and yet not even have a single Earth-like planet. So just because you have a star does not mean you're going to have an Earth-like planet because you need these other aspects. Okay, so elliptical galaxies, you're not really going to have any sort of Earth-like planet because of all these kind of danger zones and just not having the materials to even get an Earth-like planet to even exist. Okay, so elliptical galaxies off the table. What about irregular galaxies? So irregular galaxies appear disorganized and just kind of distorted. Here's a picture of one example. They do not provide a safe zone at all. They're actually worse than elliptical galaxies. They're distorted and ripped apart, and they have supernova going off kind of throughout their volume, throughout their space. So there's no really safe place that you can be where there's fewer supernova kind of like going off. Within that spiral galaxy that we were talking about, the safe place would be between the arms. So there's places where the supernova are going off more regularly and places where you'd be in a safe area. But there's no safe area away from supernova in an irregular galaxy. Additionally, these irregular galaxies, they also have gamma bursts. And so these are going to be more powerful than supernova. And if you're anywhere near a gamma burst, it's going to immediately kill any life. And so with supernova and gamma bursts, there's no place that an Earth-like planet would be able to, exist in these irregular galaxies. So in essence, the only place that you could really exist would be in a spiral galaxy. So kind of talking about this actually shows the reverse of the Copernican principle. So the propaganda of the Copernican principle was that there was a long march of science showing how common and ordinary our situation is. But really, science is actually showing the opposite. So remember in the Copernican principle, I kind of debunked or brought to light this kind of myth that had been kind of propagated throughout time and history. So really, science is actually showing the uniqueness of our situation, of our galaxy. The more threats that science discovers kind of shows you the more places that you couldn't have life. And then on the opposite side, the more we look at our place, the more ways we kind of see how we're in like a little bubble, like a little cocoon of safety. And so kind of even more science is found, discoveries, more science is learned, kind of supports the idea of, wow, we are unique, we are special because we are kind of situated in this little ideal spot. So that was kind of looking at galaxies and the three different types in our situation. But now let's look at our planet system. So let's look specifically more at our solar system. So why is our planet system unique? So when astronomers found other planets orbiting sun-like stars, they expected that their orbits would be similar to those in our solar system. So we look at our solar system, if we find another sun-like star, we think, oh, they'll probably act the same way. Now, most other planets that have been found are kind of giant gas planets. So they're going to be very similar to like Jupiter in our solar system. So we would expect them to be similar. In our solar system, Jupiter has a large 12-year circular orbit around the sun. However, interestingly, all the other giant gas planets in the other galaxies have an elliptical orbit. So very different. We have circular with Jupiter and the other ones have elliptical. Now, one thing to take into note, it's important to know what kind of orbit these giant gas planets have because they're so big, so much bigger than, an Earth-like planet. They're actually going to affect the orbit of those other planets around them. Not only Earth, but any other smaller planets. So if this giant gas planet has an elliptical orbit, then the other planets in that system are going to also have an elliptical orbit. If it has a circular orbit, then the other planets would also have a circular orbit. You say, okay, well, why is an elliptical orbit bad? So if we have an elliptical orbit, it's actually not good for life because we're going to have extremes, hots and colds. So let's think about this. If this were my sun, if I had an elliptical orbit, there would be times where I'm really close to the sun and times that I'd be further away. So it looks something like this. So closer and further away. Where if it's circular, it's going to be consistent throughout. So if I'm going to have times where I'm really hot and times that I'm really cold. Really hot, really cold. And so that's not what we really want. What we want is what we find in our system. Jupiter has that circular orbit. We have a circular orbit, which is good for life because it keeps the climate kind of consistent. So what else about our solar system? Another thing about our solar system that contributes to life was found in 1994 by George Weatherhill of the Carnegie Institute, and he found that actually Jupiter helps protect us, kind of in what's called comet catching. So like I said, Jupiter is much bigger than us. It's 300 times bigger, larger, the mass of Earth. And it kind of acts as a shield to protect Earth from any of these kind of comets coming and impacting us. It deflects comets and keeps them from coming into the inner solar system. So if you think of the way if they're coming in, it prevents it from coming into the inner solar system. And the inner solar system are those planets that are closer to the sun. Now you might think, okay, well, if a comet hits us, what's the big deal? Well, if a comet actually, collided with Earth, it could have life-extinguishing consequences. If you're not sure, there's lots of movies online that kind of talk about this, Armageddon, etc. Anything that's big, that has mass, that hits us is not going to be pretty. In addition to Jupiter helping us with comets, we also are helped with asteroids from the asteroid belt by Mars, Venus, and also Jupiter. And so here, most of the asteroids are going to be kind of prevented by Mars because Mars is on the edge of the asteroid belt. And if you kind of want to get an idea of what this would kind of look like if it were to hit the Earth, you can kind of look at the moon. So the moon's surface kind of resembles a little bit of what it would look like if it were to have gotten hit, if we would get hit by an asteroid. Now, the moon is so small, it doesn't really protect us, but you can kind of get an idea if you look at the moon of what it would do if we were to not be protected by Mars, Venus, and Jupiter from various asteroids. So here you can kind of see Jupiter, Mars mainly, both of them kind of helping prevent us from getting hit from comets and from asteroids. All right, so let's talk about where we are located in relationship to our sun and the distance. Are we close? Are we far? What does that look like? So there's this called the circumstellar habitable zone. This was invented by astrobiologists. And what this zone is this is the region around a star. So the distance, how close and how far away you could be from a star, that region, where you can have liquid water on the surface of a terrestrial planet. So this is kind of determined by the amount of light you get from the host star. So you can kind of see in my diagram here that green area is the circumstellar habitable zone. So what determines this? Why can we be too close or can we be too far away from our sun, our star? All right, so if we were too close to the host star, what would happen? So if we get too close, it's going to be obviously really hot. And if it's really hot, what happens is it's going to evaporate the water that we have both in our atmosphere and on our planet's surface. So as it starts to evaporate water and we get too much water, this is actually going to cause what is called a runaway greenhouse effect. And so the um the sun will heat it up, then we'll have evaporation, and the greenhouse gases, water vapor is one of them. And so what that does is it kind of traps in the heat more, and so then more water vapor is going to be evaporated, and it's just going to keep this cycle. So it just is causing this runaway cycle of more trapped heat and more water evaporating, which causes more heat to be created on the surface there, and then more water to be evaporated. So eventually it would just boil off all the oceans. And this is thought to believed to be what happened to Venus. So Venus is right there on the kind of cut off edge of being too close to the sun. You say, okay, so too close, no water because it all evaporates. Well, what happens on the flip side? What if you get too far from the host star? So if you get too far from the host star, it's actually going to be too cold. So here, your water is going to freeze and even carbon dioxide will freeze. And then what you're going to have is runaway glaciation. And so what happens is as the water and carbon dioxide freeze, they actually are going to repel. They're going to reflect the light that's coming in. So this is just a unique property of, you can think about it like with snow and other things of that nature, that it's got an albedo effect. And so it's going to reflect. So we want to trap some of the heat, but now we've got the water that's frozen reflecting, and then that causes more things to freeze and reflects more. And that's where you kind of get that runaway cycle that we're not really able to trap any of the heat that we want. Also, as you get further from the sun, we have to increase the carbon dioxide content in the atmosphere just to kind of try to help trap some of that sun's radiation and keep some liquid water. But if we increase the carbon dioxide content, then there's not going to be enough oxygen in the atmosphere for us to breathe, for animal life to breathe, for anything to exist. And so this is the problem if you get too far away from the host star. Too cold and also not enough oxygen. So you might say, okay, so the Earth is in a distance. Obviously, we're not too hot, not too cold because we have water, we have oceans, and we're not freezing, and we can breathe. But what if we were to move that distance? So what if the Earth's distance from the sun was moved just 5% closer or further away? It would lead to disaster. Even just a 5% change in our location, animal life would be impossible. And so this just kind of supports the fact that we're in that little sweet spot. And if we're too close or too far, even for a little bit of time, that fluctuation would, cause us to have detrimental effects to our climate. All right, so now we've kind of talked about our solar system and our location in relation to our sun, but what about our sun? What do we know about it? So our sun, here's a few little facts about our sun. So first, our sun does nuclear fusion at 27 million Fahrenheit or 50 million Celsius, depending on your preferred system, and is 93 million miles or around 150 million kilometers away from the Earth. So really, really hot and pretty far away from us. Additionally, the mass is 300,000 times greater than the Earth. So much bigger. Remember I said that Jupiter was 300 times bigger than Earth. Our sun is 300,000 times. Also, our sun is among the 10% most massive stars in the galaxy. So it's very, very massive. However, it's not the biggest it could be. If it were just 10% more massive, then it would actually have a shorter lifetime. So as it gets bigger, the lifetime will decrease. Currently, our sun's lifetime is expected to be about 10 billion years. But if it were bigger, it would be around 1 to 2 billion years. So if it were 10% more, we would have a drastic decrease in how old our star would be. Also, if we have a younger star, then the luminosity of our sun would fluctuate. So sometimes it would be brighter, sometimes it would be dimmer. And that's not something we want. We want consistency in how our sun is, shining because we want to have consistent climate. Another unique thing about our sun is it's actually a yellow dwarf. 80% of stars are red dwarfs, whereas ours is a yellow dwarf. And if you're interested, it's called a G2 spectral type. And that's just describing the type of light it is. So it means it's kind of a yellow white in color based on its luminosity class. So I said that 80% of stars are red dwarfs, but ours is a yellow dwarf. Okay, well, if most of the stars are red dwarfs, are they going to be a sun where a Earth-like planet can rotate around it or not? Well, so let's look at this. So for red dwarfs, they emit most of their radiation in the red spectrum. That's where they kind of get their name, red dwarfs. However, for photosynthesis, you need red and blue. So if we're only getting red, we're not going to have efficient photosynthesis happening, which we know is very important for life to exist on our planet. Additionally, red dwarfs are less massive than the sun. So remember when I said when they're smaller, they have decreased luminosity. And so if they're not shining as bright, we're going to need to be closer to it so that we can have the right amount of, heat balance, not too hot, not too cold. So we're going to need to be closer to have enough heat to maintain that liquid. So our circumstellar habitable zone would actually be closer if it's a red dwarf. But if we're getting closer, remember these are going to be bigger. Even though a red dwarf is smaller than the sun, it's still going to be much, much bigger than the planet. And so when you get closer to a planet that is much bigger, then what happens is called a tidal force. And so the closer you get, this tidal force gets stronger and stronger. And what that means is the planet, so if this were my red dwarf or my sun, my star, the planet would always present the same face. So even when they're rotating, it's always going to be rotating like together. So the same side is going to be facing the star the whole time. So what that means is one side is going to be lit and one side is going to be unlit all the time, which obviously is not going to be very good for life because this side would have too much heat and this side wouldn't get any. So you'd have very extremes, hot and cold, in these planets. All right, what else about a red dwarf? Additionally, red dwarfs emit solar flares. So these flares cause the star's total luminosity to vary. So it's a release of solar flare. And so when it releases, they're going to have moments of getting brighter and dimmer due to these solar flares. Now, our sun also does this, but because it is much bigger and has a greater luminosity, we don't really notice that difference. So even though the solar flares are coming off, it's kind of like a blip. We're not seeing this brighter, dimmer effect that we would see in a red dwarf. So with this, if it's getting brighter and dimmer, then it's going to affect the temperature on the surface of the planet. If it's getting brighter, then we're going to have temperature spikes. If it's getting dimmer, then our temperature is going to be lower. And that's not something we want. We want consistent temperatures on our planet. Additionally, we would have increased particle radiation in the atmosphere because of these solar flares. Now, this increased particle radiation would then come to the ozone of the planet and destroy that ozone. Once the ozone's destroyed, then the surface radiation is going to be high. And we know that we can't really be around that kind of radiation. So then life wouldn't really be able to exist. Additionally, these red dwarfs, they don't produce much ultraviolet light, UV light. And UV light is really important. It's needed to build up oxygen in the atmosphere. So what the UV light does is it actually comes in and it breaks apart water for oxygen and hydrogen. The hydrogen is light, so it just kind of goes off in space, but the oxygen is going to build up. And so if we don't have enough UV light, we're not going to get a buildup of oxygen, and we're not going to get it fast enough and a large enough amount to be able to sustain life. So this is something that we need to have. We need to be able to have this ultraviolet light. So red dwarfs, even though there's a lot of them, they're not really designed to be conducive for life. All right, so I mentioned a few things that red dwarfs don't have. Does our sun have those? So I said red dwarfs mainly produce red light, light in the red spectrum, whereas our sun actually emits red and blue light, which is needed for our photosynthesis. Okay? And this is actually a spectral image of our sun. So you can kind of see the red, blue kind of light that's being emitted. Also, our sun is metal rich. It has a higher abundance of heavy elements compared to other stars of its age in this region of the galaxy. And remember, heavy elements is a good thing. So if we have a lot more heavy elements, then you're more likely to have a planet. And one of the most important things is that our sun is highly stable. So the light output varies by 1/10 of 1%. So 1/10 of 1% over a full sunspot cycle. So over about 11 years, we only get this very, very small variation in the light output. And remember, that's good because we need a stable climate. So if the light output is stable, then we're not going to have these wild, climate changes, really hot or really cold on our surface. And then lastly, the orbit is more circular than most other stars of its age. And so by it being, by us having to have a circular orbit, it kind of helps keep Earth in that safe zone. So how the sun interacts with Earth is going to be important in the bigger scheme of our galaxy. And it keeps us safely in that little cocoon between those spiral arms. And so here we've talked about galaxies and the different types of galaxies. We talked about our solar system, where Earth is located in our solar system, and we've talked about our sun. So in the next lecture, we're going to talk more about our Earth and our moon and how is that unique, or is it unique? And so I hope you come and watch my next lecture for that. So thank you so much for coming to my talk today. Here are just a few of the references so you can follow up on those. And you can also email me if you have any questions, and you can also like and subscribe for more on science and religion.